Hi everyone, my name is Azzedine. I'm an investigator for GSK based in Stevenage. Today I'm going to talk about how we can use in silico modeling for quality by design, method development, and optimization. So what I'm going to be talking through today is a project I've used modeling software here. I'll be showing you how I went through the whole process to be able to optimize the method and make it more efficient in GSK. So just to give you an idea of how we started with this particular project, this is the method that was given initially, whereby we're using a C18 column, 45 degrees column temperature, and our phase containing THP and our phase A, and our phase B had a ratio of acetonitrile methanol and a gradient of nearly about an hour long. And what we can see is the chromatogram here on the right-hand side, and zooming into that particular chromatogram, what we can see is that we have the API, and we have its isomeric impurity next to it. What we can clearly see here, there's no resolution whatsoever between those two peaks. So the aim of this particular presentation is there a way we can try and use in silico modeling to try and optimize the separation between those two peaks. So therefore, have a resolution of at least 1.5 so what's power required for method development. The way we can do that is by going through method development by quality by design using AutoChrom. What this enables us to do using this platform is we can actually screen various different parameters between the methods. So this is things like pH, buffer, column temperature. We can then screen those conditions, try and determine what is the best condition we take forward, and then optimize various different parameters by creating 2 or even 3D models, whereby the red region is where you have the best separation that you're looking for, and the green is where you have the least separation you're looking for. And what this is a quite nice, neat process here is that you actually can create a report which gives you a summary of the whole workflow that has been taking place from start to finish to be able to do that. What we do at GSK to be able to achieve this, we actually do use a LCMS, as you can see on the right-hand side here, and I've got a bit more details on how that instrument actually looks like in the next slide. So why do we actually use this in silico modeling? Well, it enables us, first of all, to screen a total of about 16 columns at once. So we have an instrument that has 2 column compartments, which gives us a nice selectivity of various different columns, from reverse phase to UPLC and HELIC columns. We can also have up to 24 more phases, whereby A can be 12 and B can also be 12 different lines. But more importantly, we can also do peak tracking by using diode array and mass spec. So we can actually identify peaks and know where they are and how they're moving about by changing various different parameters when doing method optimization. And we can also try and identify if there is coillusion or not within those peaks by using the mass spec and UV. And one of the main primary reasons why we do use this in silico modeling, it really enables us to be more efficient at method development, but more importantly, creating shorter, more robust methods, which therefore enables us to be more sustainable going forward. How the instrument actually looks like in our labs in Stevenage is an example here, whereby on the left-hand side, at the top you have your mobile phases. We have the auto sampler, where typically your samples would be located. We have a 1290 pump with 2 valves. So we have the A1 and B1, which each can hold up to 12 lines at once. We also have 2 column compartments, which can hold up to 8 columns each. At the top, we also have a diode array, so that have a selection of various UV detection wavelengths. And last but not least, we also have a single quad mass spec attached to it as well. And this is what an overview of the software actually does look like next to the instrument as well in labs in Stevenage. So for me to be able to start off and optimize this method further, the one thing I was just trying to do is I selected 2 columns, which are quite similar to what was before, and try and see if I can just, for instance, run gradients that were slightly shorter and longer, and to try and see if I can, in some way, achieve better sort of resolution that was shown in the first slide in any particular way. So what I was able to do here, I was able to run, for example, some of those columns, but I used formic acid. What we can see, for instance, here is that I'm actually only observing 1 peak, and the peak shake actually looks worse than what it was before. I've also tried looking at using TFA. Initially, I thought I might be quite lucky and see a peak there, but that's just an extra impurity that was present, and therefore I could not even see that impurity present, which indicated that the resolution is actually worsening using those two particular columns. So at that point, I realized I probably do want to optimize the previous method a bit further and try and see if I can increase the resolution between those peaks in any sort of way. So by using AutoChrom, I was able to create various different experiments whereby I'm changing the temperature of the column from 10, 20, 30, and 50 degrees. I'm also changing the gradient time of 15, 45, and 100 minutes from 45% be going all the way to 95%, and also having a 20 minutes post-conditioning period at the end. Those 20 minutes is just enabling us to make sure that the column is ready for the next injection and it's stabilized within those 20 minutes. I'm using a typical C18 column, and what I've done in this case, I'm trying to use a UPLC column by using a 2 micro particle size column here. I'm also fixing the same mobile phases as I showed at the beginning of the presentation at this particular moment. When I ran this, I was able to run the model, but actually that impurity there wasn't an isomeric impurity. That was an excellent impurity I could see, but the main impurity I'm looking for, I still could not observe running those particular conditions. So what I'm then trying to do is, I thought, how about in this case, instead of using a UPLC column, I repeat the experiments I've shown initially, but using a different column length. So instead of using a UPLC column, how about use a typical HPLC, so 3 micrometer particle size, but also a 250 millimeter column length. So we're using now a longer column than what was actually shown at the beginning of the presentation here, but I'm still making sure that I use the same wire phases as well as per provided. When I run this particular conditions and experiments, again, I couldn't observe any sort of impurity when I ran those experiments, which was a bit concerning. However, what I realized is that a trick we've actually used to be able to improve the resolution between those two peaks is that we can condition the column for a certain amount of time just once when the column is first installed to improve the resolution. So normally about 0.2% TFA is used to condition the columns, and then we can run the experiments, but I haven't done that in the case. So what I've then done, I try and repeat those experiments. However, instead of using 0.2%, I increase the concentration to 0.4% TFA in water, and not only just condition it for 24 hours, but in this case for 48 hours, and using a column temperature of about 45 degrees. So then I thought, okay, I would then run these conditions again at 10, 30, 50, but using gradient of 30, 45, and 90 degrees. And as I mentioned earlier on, trying to also have that conditioning of the column of 20 minutes at the end of the gradients. What we're able to see here, so this is LCSIM, is I was able to generate some models. I'll go a bit more details of what this actually represents, but basically in red is where you have the best resolution of your peaks of interest, and in blue is where you have the least resolution of those particular peaks. And what we can see here, I can now clearly see my isomeric impurity and my peak of interest, my API here as well. What I'm also able to do using LCSIM, I'm actually able to generate a series of various different methods. So what that means is I can actually modify the column temperature and also modify the gradient. So how fast or how steep the gradient is changing, and also adding hold times in within to try and see what will be the best method that will give me the best resolution between those peaks. So I was able to then create 6 methods from the model we generated, and I was able to transfer down to the instrument. So for purpose of time, I'm not going to go through every single method I was able to generate, but I'm just going to show you the best one that gave me the best resolution out of them. And the one actually quite stuck out was the method 1. And this is version 1, which was about 37 minutes run. So on top we have the blank. At the bottom here, we have our sample. And what we can see actually here is that at the bottom, now we can see an osmotic impurity, and we can see our apparent peak, but the resolution is about 1.53. And typically, you need a minimum resolution of 1.5, so we're just on the borderline of the minimum resolution we need. If you look at the left-hand side, the gradient will go from 55, 45, all the way to 95, and then switching back. What we can see when we run this particular method, we can see a large peak at the front, and this is basically a carryover of the previous injection. what this actually indicates is that we're not letting enough time for the column to condition at the end for the next injection. So what I was able to do then is able to trial various different versions of this particular method. And version 3, what we can see, we've increased that particular runtime to 45 minutes. But now that people were seeing it previously is actually now observed in the whole injection rather than the carryover in the next injection. And even increasing the gradient time, we're still seeing a nice resolution of 1.53. Now the question is there any way I can try and improve that moving forward? But one thing I realized is once I've run this particular method over the weekend for over 100 injections to try and determine the repeatability and robustness of the method, what we can now see is that the impurity and the apparent peak are actually coeluting, which indicates that potentially this method could not be robust due to the conditioning that we used of the column. As I mentioned at the beginning, what I did do in this case, I conditioned the column for 2 days using 0.4% TFA, which is quite a lot. What I then did is I got a brand new column, but then in this case, conditioned using 0.1% TFA, and a different column also conditioning using 0.2% TFA. But instead of doing it for 2 days, I've only done that for 24 hours. And what we can see now, when we zoom in using the 0.1% TFA and using the same gradient as I showed you early on, now the resolution actually slightly improved to 1.55. The peaks you can see at the front here are just a contamination of more phases. I was able to get rid of those when you're going to see later on, so please ignore those. But what we can see here is actually the resolution has slightly improved by using less acidic phases to condition before the column is used. One thing I was quite interested to see and to determine if the column is good for use is also repeatability. So if I inject my sample 6 times, do I observe any sort of peak shifting or not, or are the peaks constantly the same at the retention time? What we can see, even though the change in retention times is quite small, we can see there's a slight shift in retention time, as you can see here. And I guess what I want to do in the next steps of this optimization and development is that any sort of way I can make sure that this peak shifting is reduced in any sort of way. So what I then did is I also took another column and I conditioned that column using 0.2% TFA rather than 0.1%. And again, we're still seeing a resolution of 1.54, which is quite similar to what we've seen, but which is better than what we've observed to date from the original method. Now I thought, okay, how can I use Silico modeling to try and improve the resolution between those peaks further? So how about we then create models whereby we're correlating TFA and the ratio of the mobile phases or the solvents in this case. So on my y-axis, how about I change the TFA concentration from 0.06, 0.07, and 0.1%? And on my x-axis, how about we go from the far left using 100% methanol and then going to 70-30, 50-50, 30-70, and 100% acetonitrile, so a mixture of those two. And we're using a gradient of the version 2 of the method I've shown previously. I'm still using the same column, which is about 250 millimeter length and 3 micro particle size. And in this case, I'm using the column that condition using 0.1% TFA in water over 24 hours at 45 degrees. What we're able to create running those experiments. So as I mentioned, on the y-axis, we have the mobile phase pH, so in this case, the TFA concentrations. And on the y-axis, we have methanol and acetonitrile. So going from 100% of methanol all the way to 100% acetonitrile. So that's what we've seen before when it came to the temperature gradient and column temperature as well, is that where it's red, we have the best separation, where it's blue, we have the least separation. However, keep in mind, even at the blue state, we're already having a resolution of 2.13, which is still above 1.5. But one thing you also want to keep in mind is that you also want to use conditions that are aligned to the column specification. So you don't want to use TFA concentration that's, or pH level that's way above or way below the limit of those columns that you want to use. And I think to also consider is if you're using 100% methanol, you're probably going to have longer retention times. So you're probably going to try and use acetonitrile if you can to try and balance retention time and the peak shapes as well. After trying out various different combinations of those conditions, what was able to come with is finally method 1, version 4. So this is using the 0.1% TFA in water column. And what we can actually see here is that we have a runtime of 48 minutes and 30 degrees using a flow rate of 0.7 minutes. So this is the blank injection. At the bottom of it, we have the sample injection. And now we can see the resolution between our API and osmotic impurity. And now we're seeing a resolution of 1.93. So this is an improvement compared to what we've seen before, which is about 1.55. What we're also able to do is, how about if we actually transfer this method onto a 1260? So the previous slide was using a 1290. So how about we use a 1260? What does that actually mean? So how can we go from using a high pressure instrument to a lower pressure instrument and make sure we still have that selectivity present and resolution? So as you can see here, even using a 1260, using the same method, we're seeing a resolution of 1.87 as well. Now, the other question we also wanted to check is, how about repeatability? As I've showed you in the past, a couple of slides ago, is that we could see those peaks were shifting over time. Now we can see there's a nice overlay across those peaks there. We also transferred that across the 1260, so HPLC instrument, what we can also now see there's actually a nice perfect alignment across all those repeated injections. The one thing I also wanted to check to make sure the method is good for and fit for purpose is how is a signal to noise. So can I do a sensitivity check? So I've done in this particular case here, I prepared a sample at a normal concentration of 0.05%. And what we can see on a 1290, we're having a resolution of signal to noise response of 10. When I transferred this onto a 1260, so a HPLC, we're now seeing signal to noise of a value of 12, which is slightly improved compared to UPLC. And last but not least, what I was able to do then is then overlay my sample injection against the blank and integrate every single peak present there to have an idea of what sort of impurities we have present and the levels of them as well. And this is giving an idea of how the chromatograph might actually look like on a 1290. And I also repeated that and done the same as well on the 1260, which you can see we have a nice flat baseline, but more importantly, we can see a peak purity of about 98.1% there present. So in summary, what we're able to do here, I'm able to create this method on the 1260 and 1290. And this is summary, I guess, of the parameter we're able to identify and change. So now we're using the same column, but what we've done is actually use a longer column rather than a 150. Using column temperature of 30 degrees, which is well within the specificity of this particular column. Now for TFA, we're using 0.06% TFA in water. And mobile phase B is 50-50 acetonitrile to methanol ratio. The flow rate is still 0.7. But now what we've also done now, instead of having a gradient of 55 minutes, we're able to shorten that to 48 minutes. But more importantly, what we're able to do is going from having no resolution to having full resolution between our osmotic impurity and our apparent peak as well. One thing to also consider, it's quite interesting to see, the conditioning of the column. So what we mean by this is that you condition the column when you first receive it, and this is just a one-off. So you do that for 24 hours at 45 degrees. And what we can see is that once we've done that with 0.2% TFA, we're getting a resolution of 1.83 on the UPLC and 1.66 on the HPLC. However, if we do the same conditioning using 0.1% on a different column, we can see there's a slight improvement of resolution by using a UPLC and a HPLC compared to using 0.2%. And the reason why is because if you use a 0.2% TFA, the column is not able to sustain such a low pH, which means over time you're potentially damaging the column by conditioning it using 0.2% over 24 hours. One thing I also haven't shown here is that what we're also able to do by using a particular method and using a 0.2% conditioning over 24 hours, I was able to repeat this particular experiment for over the weekend. So I think it was over 100 injections. and the teeth and the resolution hasn't changed or whatsoever. So what that indicated is actually the method is robust and has good repeatability from what we're able to develop using the Silico modeling software. So to summarize, what I have done initially is I have looked at screening various different column chemistry under C18, but I couldn't get better resolution between those peaks. What I showed you at the beginning, we couldn't see any sort of resolution by using the long or UPLC column, but however, we're able to achieve better resolution within those isomeric impurity and apparent peak by conditioning the column using 0.2, 4, and 2% TFA in water. We also, what we also observed is conditioning the column using 0.4% TFA in water over 48 hours actually damaged the column over time. And this indicates that obviously the pH is way above the limit of the column itself. One thing I also tried to do is adding TFA onto mobile phase B. However, doing that has also indicated there's no improvement in the resolution, so therefore it was taken off. We also able to optimize further resolution by generating models, not on the column, just not only using the column temperature and the gradient, but more importantly, looking at the TFA concentration of mobile phase A and the ratio of methyl and acetonitrile. And what we're able to do with that, we're able to increase the resolution from 1.55, as you saw, to about 1.93. And then what we also showed is actually using conditioning of the column of 0.1% TFA over 24 hours was better and provided better resolution compared to using 0.2% TFA in water, simply because 0.2% TFA in column TFA in water is below the specific limit of the column and therefore damages columns over time. So in summary, what we've seen is using 0.06% TFA in water and 50/50 acetonitrile water, we're able to improve the resolution by using 0.1% TFA condition column from 1.55 to about 1.93 on a UPLC and about 1.88 using HPLC. Thank you for listening. If you have any questions, I'd be more than happy to answer them.